This is the lecture for section 9.2. In the previous section, we learned about the basics of the idea of a hypothesis test or a statistical test of significance. In this section, we're going to dive in deep into the particulars for doing a test for population proportion. We should know about how to check make sure the conditions are correct and been accounted for. We should know how to conduct that significance test and we see the relationship between confidence intervals and significance tests. So let's think back about the stuff that we learned in 9.1. We learned that we have two hypotheses, one called the null hypothesis or the H-naught claim, a claim that is a claim of no difference or a claim that we don't think is actually true. We also have a HA claim, the alternate hypothesis, which is the claim of what we're trying to prove is true. We know that there's this thing called the p-value, the probability that assuming H naught is true, that we would see a sample statistic as extreme or more extreme by pure chance alone. And we know that we can compare that p-value to an alpha value. And when our p-value is low, it represents a lot of evidence against the H naught claim. Low p-values give us the ability to reject H naught as a truthful claim and accept HA as a truthful claim. When we don't have enough evidence, when we have a high p-value, we say that we fail to reject H naught. So let's do this in the context of those free throw shooting examples. Recall our basketball player who claims to be an 80% shooter. We say, we don't believe you. So we go and do a simple random sample of 53 throws. And out of those 53 throws, he makes 32. The p-hat value is 0.64. The question is this sample, 0.64, an unusual occurrence, or is that occurrence of 64% or more extreme, so low that we think it's unlikely to have happened by chance? Our H naught claim would be that the population proportion of all this players free throw shooting is 80%. Again, we don't believe that the H naught claim is true, but we say that for the purpose of running this procedure, let's pretend that it is. What we really think is that this player's free throw shooting ability is less than 80%. We talked about in the confidence interval chapter about checking conditions to make sure that the conditions are met. And in this case, we still have the same three conditions. Condition number one, that the sample is random, which leads to unbiased sampling. Second condition that we check is normal. Do we think that this p-hat value is coming from a normal distribution? We check that by seeing if the expected number of successes, in this case, 50 shots and 80% shooting ability, results in 40 successes. 40 is bigger than 10. We're good. So we give a little check mark that we meet that. We said that we had a simple random sample. We check mark for that as well. And then the expected number of failures, 50 times 20%, which is 10, and 10 is also greater than or equal to 10. Our last check is a check of independence. Do we think that the observations are independent? Now, if we're drawing without replacement, we may check the 10% condition. Is our sample less than 10% of the entire population? In this case, since we're looking at individual trials, do we think that the individual trials are independent? Let's assume that they are, right? When we assume that the H naught hypothesis is true, then we could say that we know something about the sampling distribution of the p-hat values from which our sample came. We have this normal distribution because we checked the normal condition. We know that it's centered at 0.8 because we assumed H naught was true. We have a standard deviation of about 5.7%. Again, notice that we use the H naught p-value in that calculation because all of our calculations are done assuming that it's true. And we found that the outcome of 0.64, 64% or lower, makes up a really small tail. It looks like it's a really rare event to have 64% or less by pure chance alone. Let's look at a way of creating a little bit more of a procedure for doing this calculation. We are going to calculate a test statistic. Now, generically, a test statistic measures how far our sample outcome is away from what we expected, measured in standard deviations. So in this particular instance, we know that we have a statistic that goes along with our work, and that statistic is a p-hat. We know that we have a parameter from the H naught. We can call it P, or we can call it P naught. That's the proportion coming from the H naught claim. And we have a standard deviation, which in this case, we would say is P naught 1 minus P naught over N. Now, in this case, the p-hat value is 64%. So I might say, how far is 64% away from our assumed proportion of 80%? And then the calculation of that standard deviation. And if we put those numbers into our calculator, let me bring my calculator up. We could say that, let me start a new document here so we can get a nice clean. Okay, we can do our calculation. I'm going to go control division to get a fraction, 0.64 minus 0.8, and we'll divide that all by the square root, and I'll put another fraction in, 0.8 times 0.2 all over 50, our sample size. And when we do that, we get a z-value of negative 2.83. Okay, now we have that z-value, we can calculate a p-value. We could say, what's the probability coming from a standard normal distribution, in which the mean is 0 and our standard deviation is 1. What's the probability of getting this z-value or less by pure chance alone? So what is the probability of a z-value of less than negative 2.83 by pure chance alone? Well, we would do this on the calculator using a normal CDF function. And we would say we want from negative infinity to negative 2.83 with the mean being 0 and the standard deviation of 1. And of course, we document this. This is my lower bound. This is my upper bound. This is my mean. And this is my standard deviation. So let's go back to the calculator and put that in and see what we get. So menu, probability, which is option number 5, distributions, 5 again, normal CDF, lower bound infinity, negative infinity, upper bound of negative 2.83, and then it defaults to a mean of 0 and a standard deviation of 1. So let's go ahead and hit enter, and we get that p-value is 0.0023. And 4 decimal places is about where we will stop for our accuracy. Negative 0.0023, certainly less than 1%, makes me suspicious that this person is not telling the truth. So let's summarize what we're doing here. We're going to call this a four-step process where we look at the various aspects. This is similar to what we talked about for confidence intervals. Our four steps is to talk about what we're going to talk about, what population are we pulling from, what parameter are we investigating. In our plan, we check our conditions that are appropriate for our method. So in this case, we'd say, hey, our method is a one sample z-test for population proportion, and the conditions are random, independent, and normal. In step 3, the do step, we calculate the test statistic. We calculate, in this case, the z-value, and from that z-value, we calculate the p-value. And then the final step, we interpret that p-value. We compare it to our alpha value to determine whether we are going to reject or fail to reject our H0 claim. Now, when we get the z-value, it is not entirely clear how to calculate the p-value. We really need to look at the HA claim to determine what the p-value is being calculated. So when we get to the point where we're calculating the p-value, we're going to look at our HA claim to determine what we're doing. For example, if our HA claim is that the population proportion is bigger than the p-naught, then we're doing an upper tail test, in which case the z-value and then infinity will be the first two values in our CDF function call. If we're doing a less than, then it's going to be a CDF in which we do negative infinity and then up to that z-value. Now, when we say not equal to, the calculation's a little different. We will take the absolute value of the z-value and go to infinity. And that will get us this part of the tail. But you'll notice there's an equal and opposite section for the negative z. And that's why when we're done, we're going to multiply that probability by 2. Right? Remember, these are only valid calculations if we know the distribution is normal, and we only know that if we check to make sure that the number of successes and the expected number of failures are at least both 10. And that we meet the independence condition, which is that the population is at least 10 times as large as the sample if we're sampling without replacement, or that every event is independent within itself. Let's look at this four-step process in an example problem. A potato chip producer has received a truckload of potatoes from its main supplier. If the producer determines that more than 8% of the potatoes in the shipment have blemishes, the entire truck will be sent away and will get another load. A supervisor selects a random sample of 500 potatoes from the truck. An inspection reveals 47 of the potatoes have blemishes. Carry out the significance test at the alpha 0.10 significance level. What should the producer conclude? So in step 1, remembering that every single one of these questions is a question about inference, we are going to say, we better talk about what population we're inferring onto. In this case, the population are potatoes on the truck. And that the parameter that we're investigating for that population is the proportion that have blemishes. Our H naught claim is going to be that everything's okay and that the population has 8% blemishes. But what we really want to know is, should we reject the truck? We want to know, is there more than 8%, that have blemishes? And we've been told that the alpha value, the required amount of evidence that we need to send the truck away is 10%. In our plan, we'll start with our method. And our method name, as said before, is the one sample z-test for population proportion. The conditions for this test is that we need to be random, and the fact that it was a random sample was stated in the problem, which gives us the evidence that we need to say, yep, we're okay there. We need to know about independence. We're sampling without replacement. So we ask, is the sample size of 500 potatoes less than or equal to 1/10 our population size? And I think it is safe to assume that there is at least 5,000 potatoes on a truck. All right, so give ourselves a check mark there. Normal condition, and that is n times p, and I want you to write all of this out every single time, is n times p, which is 500 times 0.08, all right? And that number is, go to the calculator, that number is 40. 40 is definitely greater than or equal to 10. So we get a check mark there. And then n times 1 minus p, the expected number of failures, which is 1 minus 0.08, which on the calculator will be 500 times 0.92, and that's 460. And that number is also greater than or equal to 10. Of course, those two numbers add up to 500, just like we expect them to. So we meet all the conditions for the test. Let's go to the do step. In the do step, we will be carrying out, finding our test statistic and our p-value. We start with the fact that our p-hat value is 47 out of 500. And 47 out of 500 is 9.4%. Our z-value is p-hat minus p-naught over p-naught times 1 minus p-naught over n, or in this case, 0.094 minus 0.08, all divided by the square root of 0.08 times 1 minus 0.08 divided by 500. So 0.094 minus 0.08 divided by, put in a square root, put in a fraction, and that again was 0.08 times 0.92 all over 500, meaning that our test statistic is 1.15. 2 digits is fine there. Now let's calculate the p-value. The probability that z, the z-value that we just calculated, and now we look back to the H naught claim, and we say, hey, z is greater, or we have a greater than there, so greater than 1.15, and we'll use a norm CDF, and this is a greater than. So imagine again that we're here centered at 1, sorry, centered at 0, standard deviation of 1, and here we're at 1.15, and we want to know the greater than. So that is 1.15 to infinity with a mean of 0 and a standard deviation of 1. And again, document everything, lower, upper, mean, standard deviation. Let's go ahead and put that in the calculator. Menu, distributions, sorry, probability distributions, normal CDF, negative, 1.15 to infinity, with 0 and 1 being our mean and standard deviation, and we get a p-value of 0.1251, which is, again, 4 digits accuracy there, please. And now we're ready to conclude, to interpret our p-value. And that is because the p-value of 0.1251 is greater than our alpha value of 0.10, we fail to reject H naught. We compared the p-value to the alpha value. P-value is larger, which means we don't have a lot of evidence, so we fail to reject H naught. Now we need context for our statement. There is insufficient evidence to suggest that the true proportion of, now we got to mention our population, potatoes on the truck. Now we mentioned what is it we're investigating, that have blemishes, and then we restate the H naught claim. Is greater than 0.08. What does that mean? The truck should be accepted. And let's get all those potatoes off of there and make delicious potato chips. All right. There's our 4-step process from beginning to end. What are we doing? Step 1, do we meet the conditions for the test? Step 2, calculations of a test statistic and a p-value in step 3, and then an interpretation of that outcome in step 4. All right. Here's a check for understanding to make sure that we really do understand the procedure for doing a one sample z-test for population proportion. On shows like American Idol, contestants often wonder if there's an advantage to performing last. To investigate this, a random sample of 600 American Idol fans were selected to view audition tapes of 12 never before seen contestants. For each fan, the order of the 12 videos was randomly determined. Thus, if the order for performance doesn't matter, you would expect 1/12 of the fans to prefer the last contestant they view. In this study, 59 of 600 fans preferred the last contestant they viewed. Do these data provide convincing evidence that there's an advantage to going last? Well, again, since this is an inference procedure, let's start by talking about what is the population and what are we measuring about that population. The population in this case is American Idol fans. And the parameter of interest is the proportion that prefer the last contestant. Our H0 claim is nothing special is going on, and that is the proportion that prefer the last contestant is 1/12. Our H&A claim is that going last provides advantage, so the proportion would be greater than 1/12. And because they didn't give us an alpha value, we're going to use the standard alpha value of 0.05. In the plan step, our method, once again, is called the one sample z-test for population proportion. That we have conditions for this test. One of them is random, and the random is stated in the problem. So we give ourselves a check mark there. That we have independence, that our sample size of 600 represents less than 1/10 of the population size, and we think it can be safely assumed that there are more than 6,000 American Idol fans. And then the last, our normal condition, n times p, and we're going to write that down every single time, is 600 times 1/12, which is our p0 value. Let's get the calculator up. 600 times 1/12 is 50. And 50 is certainly greater than or equal to 10. N times 1 minus p is 600 times 11/12. And that should be 550, because the two numbers have to add up to 600. And then that number is also greater than or equal to 10. So we meet all the conditions for the test. Let's go on to the do step, the calculation step. Our p-hat value was that 59 out of the 600 people in our sample said that they liked the last performer, and that ends up being 0.0983. We're going to go 4 decimal places there. And by the way, p, which was 1/12, that is 0.0833. And there are our two numbers for our calculation of the test statistic. P hat minus P naught over square root P naught 1 minus P naught over N, or in this case, 0.983 minus 0.0833 all over square root of 0.0833 1 minus 0.0833 all over our sample size, which is 600. So control division, 0.0983 minus 0.0833 divided by square root, and then control division, get another fraction, 0.0833 times quantity 1 minus 0.0833, and divide that all by our sample size, giving us a z-value of 1.33, round that to 2 digits. Now, remember that that z-value is coming from a z distribution with a mean of 0 and a standard deviation of 1. Here we are at 1.33. And as we look again at the direction of our HA greater than, we are shading above there. So we're asking, what's the probability that a Z is greater than 1.33? And that's going to be a norm CDF with 1.33 being the lower bound, infinity being the upper bound, 0 being the mean, and 1 being the standard deviation. So here's our lower, here's our upper, here's our mean, and here's our standard deviation. Menu, distributions, probability distributions, norm CDF, 1.33, upper bound, infinity, and everything else is good. And we've got a p-value of 0.0918. All right, time to make our conclusions. Again, we're looking at the p-value, and we think because the p-value of 0.0918 is greater than our alpha value, which we said was 0.05, we fail to reject H naught. Let's add context. There is insufficient evidence to suggest the true proportion now we have to mention our population of American Idol fans. And then we say what we measured, who prefer the last contestant. Notice that all this is a rewrite of the step 1 is greater than 1/12, which again comes from our HA claim. So there's our 4-step process for that one. Now this is a one-sided test. We call this an upper tail test, we're going to do another one. We're going to do another one, but this one's going to be a two-tailed test. Let's take a look at this one. It says, according to the Centers for Disease Control and Prevention, the CDC, 50% of high school students have never smoked a cigarette. Robert wonders whether the national result holds for his large urban high school. For his AP Stats project, Robert surveys a simple random sample of 150 students from his school. He gets responses from all 150 students, and 90 say they have never smoked a cigarette. What should Robert conclude? Give appropriate evidence. Well, again, we'll start by saying this is an inference procedure. So what's our population? Our population is students at Robert's school. And what are we measuring about these students? It's our parameter of interest. And that would be the proportion who have never smoked a cigarette. Our H naught claim is a claim of no difference, that the proportion for Robert's school is the same as the national, but Robert isn't sure it's true. So we're going to say our H naught claim is are they different? Could they be different bigger? Could they be different smaller? We don't know. And alpha value wasn't given, so we'll choose the standard alpha value of 0.05. Our plan, our method continues to be the one sample z-test for population proportion. And under random, random is stated in problem. So we meet that condition. Independent. Now I don't know n, which is 150, is less than or equal to 1/10 of the population size. But I'm going to give a check mark because I think it's safe to assume that more than 1,500 attend a large urban high school. Only 2 I was in school. All right. And then our normal check. Remember we say n times p, which in this case is 150 times 0.5, which is 75. 75 is greater than or equal to 10. Get a check mark there. And then n times 1 minus p, which is 150 times 1 minus 0.5, which is still 75 and is still greater than 10. So we meet all the conditions for this test. Let's go ahead and do our calculations. Calculate our p hat value. Remember, 90 out of the 150 said that they didn't smoke at Robert's school. That was the number in his sample, and that's 0.6. Remember, our p naught value is 0.5. Our z value, p hat 1 minus p naught, square root p naught 1 minus p naught over n, or 0.6 minus 0.5 over the square root of 0.5 times 0.5 over 150. So we're going to go 0.6 minus 0.5 square root division 0.5 times 0.5 all over 150, giving us a p-value of 2.45. And again, we're okay with rounding that to 2 digits. Now, when we talk about the p-value, I want you to recall that we said it is unusual and different, not in any particular direction. So here we are at like 2,745, and this tail right here would be us being different on a big scale, and there's an equal and opposite on the other end. And the way we're going to calculate, or the way we state this, we'd like to know is the probability that the absolute value of z is greater than the absolute value of 2.45. Now to calculate that, we're going to still use a norm CDF. And we're going to look at just this end first, and that is from 245 to infinity based on a mean of 0 and a standard deviation of 1. But because these two areas are going to be the same, we're then going to multiply that number by 2. So here we go. Menu, probability, distributions, norm CDF from 245 to infinity. And again, 0 and 1 are good. Okay, and then we're going to take that number and multiply that by 2. And we get 0.0143. All right? So each of these are about 0.007, and then we double it to get the two tails. And now we're ready for our conclusion. Because the p-value of 0.0143 is less than the alpha value of 0.05, this time we reject H naught. Let's add context. This time there is sufficient evidence to suggest that population mentioned now, or sorry, that the true proportion of, and again, students at Roberts School, that's our population, that never smoked a cigarette. That's what we're measuring about them. And now we restate the H naught claim is not 0.5. Or we could say is different than 0.5. And there's our four-step process for that problem. Okay, now there's a connection between this four-step problem that's a two-sided problem, a two-tailed problem, and confidence intervals. If we were to do the same process and do a confidence interval with the number of successes being 90, the number of failures being 60, we would say that again, p hat is 0.6, and we could have calculated a 95% confidence interval. 196 square root 0.6 times 0.4 over 150. Now I've already done this calculation. It ends up being 0.5216 and 0.6784. Our conclusion, assuming that again we went through and did the four-step process and found that the conditions were met, is that with 95% confidence, we believe the true portion, and again, mention the population of students at Roberts School that never smoked a cigarette is between the two numbers that we just stated, 0.5216 and 0.6784. Now, let me kind of put this in another way. Do we think that do we think that 55% may be the right number? Well, it's in the interval, could be. Do we think that 53% could be the right number? No, it's in the interval. Do we think 50% could be the right number? No, it's not in the interval. So the same conclusion that we said about rejecting the idea that it's 0.5 from the hypothesis test is also shown up here. The fact that 0.5 is not in the interval is the same kind of evidence that gives us the small p-value. Let's take a look at this in a slightly different way. When we get p hat values that are far enough away from the value of p hat that's spoken in the H naught claim, when we do an interval, the confidence interval, we don't get to go back and reach that mark. In other words, every single p hat value that happens to be in the reject H naught area is also having a confidence interval that doesn't reach back to the proposed p-value or to the proposed population proportion. But if a p-hat value is in the fail to reject area, this vast middle here, its confidence interval would be enough to capture that true mean. What's being saying here is if I do a confidence interval and the p naught value is not in the interval, it's the same as doing a reject H naught on a two-sided hypothesis test, right? So we can not only learn from the confidence interval which side the p hat value lands us on, we can also find out whether it's significant without even doing the calculation of the p-value. Now, this is going to work such that a confidence interval, a confidence level of 95% is going to be the equivalent of an alpha value of 0.05. That if we had a confidence level of 99%, then the alpha value that we would be rejecting in is at the 0.01 level. If we had a confidence level of 90%, it'd be equivalent to rejecting at an alpha level of 0.10. And that concludes our discussion of test for population proportion.